All right, all right. So here's this problem we're looking at. Here's this problem we're looking at. Again, we have a paraboloid. It intersects the plane x equals 1 in a parabola. Again, the plane x equals 1 is a vertical plane. It cuts the paraboloid vertically, so it has to cut it in a parabola. We want to find the parametric equations for the tangent line to this parabola at the point 1, 2, -4. Now, 1, 2, -4, that point, of course, is on the paraboloid. And since x is equal to 1, that point is going to be on the parabolic cut of the paraboloid cut by the vertical plane x equals 1. So when you think about it, x equals 1. Okay, this paraboloid is going to be a paraboloid. This cut is going to be a paraboloid where across like horizontally, you're going to have the y-axis. Okay, and one moment here. Vertically, you're going to have a z-axis. So vertically is always the z-axis, but the paraboloid moves across with respect to the y-axis. Okay, so to get the, like for this particular parabola, let's say the point of intersection is down here, okay, and hold on. And this is your line of intersection here, okay. To get the slope here, okay, the slope of this tangent line, okay, you got delta z as your rise and delta y as your run. So finding the partial derivative of z with respect to y is going to be very, very important in regards to getting the slope of the tangent line to this parabola at the point 1, 2, -4, which say is down here. Is this clear? Is this clear? Are there any questions on that? Okay, Ellie's good. Good so far. Hyunwoo's good so far. All right, all right. So now we go to find the partial derivative. The partial, so like here, let me go back here. If we look at the paraboloid, when we compute the partial derivative, of z with respect to y, that means we hold everything constant except the y. Okay, so the derivative of 6, of course, is 0. The derivative of x is 0. The derivative of x squared is 0 because we're treating the x like a constant. So the only thing that means then the partial derivative of z with respect to y is equal to -4 times y, which is the derivative of the -2y squared. And so since the point that we're trying to find the tangent line at, the point on the tangent line is 1, 2, -4, that means then that the partial derivative of z with respect to y at the point 1, 2, -4 that's going to equal -4 times 2, which is -8. Okay, and that leads us into our next page. Now, the next page, I want you to ignore this picture. Okay, I'm not comfortable with that picture right now, but I am comfortable with what I have here. So the partial derivative of z with respect to y at the point 1, 2 is equal to -8. Okay, and I guess on the previous page, I guess what I should have written is I should have written it with this notation. Okay, so the partial derivative of z with respect to y at 1, 2 is -8. And now that means then that the rise in the z direction is -8 when the run in the y direction is 1. Okay, and therefore I can get the parametric equations for my line because well, x, the point of intersection, right, is 1, 2, and -4, and the direction that the line of intersection goes. Okay, if you think about a vector that gives direction, this 1 is 1 plus 0t. So the vector that gives direction is 0, 1, -8. In other words, this vector here is parallel to the tangent line. The tangent line goes in this direction, in the direction of the vector 0, 1, -8. And of course, the tangent line passes through the point 1, 2, -4. Hence, these are your parametric equations. Okay, and again, don't worry about the picture, ignore the picture. Are there any questions on this? Okay, well, if you're feeling good with that, let's continue talking a little more about section 11.3. So I want to go to the ebook. Just give me one moment to bring the ebook up. Last time we talked about partial derivatives, first partial derivatives, and we did an example, but you can have higher partial derivatives. Just like in calculus 1, when you have a first and second derivative, you can have higher derivatives, higher partial derivatives. And what you see here are second partial derivatives and the notations that go with them. We'll look at an example. But what you have here is you have Newton's notation and Leibniz notation. Okay, Newton's notation and Leibniz notation. So for example, in the first row there, they have f sub xx. That means take the partial derivative with respect to x, and then differentiate that partial derivative with respect to x. Okay, now again, you're holding all the other variables constant. And now the second line is the second partial derivative of f with respect to x and y. So what you do is you see there on the second line, you take the partial derivative with respect to x first, and then you take the partial derivative with respect to y. If you change the order and have f sub y x, then you take that's on the third line, you take the partial derivative of f with respect to y, and then that function, you differentiate that with respect to x. Okay, so let me show you an example here. Let me show you an example. Let's look at example 6. Here, they want you to find the second partial derivatives of this function. So, of course, first, before you can get to second partial derivatives, you have to do the first partial derivatives. Well, the first partial derivatives, the partial derivative of the function with respect to x equals 3x squared plus 2xy cubed. Again, so that highlighted, those two highlighted partial derivatives, on the left, when I differentiate the function with respect to x, what am I holding constant? What am I holding constant there? For that f sub x, which is the partial derivative of f with respect to x. What variable am I holding? That's right, Charles, I'm holding the y constant. So if I hold the y constant, then when I differentiate, then like above there, the function, the negative 2y squared, the derivative of that is 0 when I'm differentiating with respect to x, because I'm treating the y as a constant. Now, on the other hand, the partial derivative of f with respect to y, okay, is 3x squared y squared minus 4y. The partial derivative of f with respect to y, I'm holding the x constant. And so like the x cubed in the function drops out when I differentiate with respect to y. Now what I want to do is I want to do higher partial derivatives. And here are the higher partial derivatives. Take a look, just take a look. Hold on here. Yeah, you can see everything you need here. Let me know, please, if you have any questions. I just want you to look at what you see in front of you and let me know if you have any questions on why those second partial derivatives are the way they are. And are there any, and you can see the advantage of the Leibniz notation as well. But are there any questions? Who's feeling good so far? Okay, Ellie's good and Charles is good. Okay, all right, Yunu. Juliana's good. All right, very good, very good. Well, do you see anything interesting about the two mixed partials? Mixed partials are when you differentiate with respect to x and then with respect to y, or when you differentiate with respect to y and then with respect to x. So f sub xy, f sub yx. Do you see anything interesting about those mixed partial derivatives? They're equivalent. That's right, Ellie. And that's a fact. Well, Charles, it doesn't have to do with commutative, but in fact, these mixed partials are going to be equal. And that's due to a theorem called Clairaut's theorem. Okay, that's due to a theorem called Clairaut's theorem. All right, so just keep that in mind. Let's look at another example here. The more examples you see, the better off. Okay, let me go here to this example 7. Now here, oh my goodness, you're doing higher derivatives. That's correct, Charles. That's exactly correct. For all cases, that's correct. Very good, very good. So look here. Here they want you to do a fourth partial derivative. So here your function, you have a function of x, y, and z, which equals the sine of 3x plus yz. When you differentiate with respect to x, okay, so like in the solution here, let me see if I can, in the solution, okay, the first step is to differentiate with respect to x. Okay, let me just do one thing here. One moment, class. One moment. Take a look at it. Take a look at it. Okay, let me show you something here. I think this will help you. I think this will help you. Let me show you something. So what we're trying to do here is we're trying to differentiate, compute a fourth partial derivative. Now see what you can do, you can sort of treat these like exponents, these subscripts. So I mean, you know, they're not exponents, right? But if you raise to a power, if you take what's in parentheses here and you raise it to the zth power, what do you do with exponents when you raise to a power? They're subponents, but like what I'm trying to say is, like, if you have like x squared and you raise it to the 5th power, what's x squared to the 5th power equal to? Good, x to the 10th, that's right. So you multiply the exponents. So what I'm trying to do is in this example 7, there's an order in which they are taking their partial derivatives. I want you to understand why they're doing that in the order. So what I'm trying to do is I'm trying to say, well, you know, if we think of this kind of like as pretend we're multiplying these exponents, quote exponents, by this exponent, we multiply the exponents and get this. You see there? See what I'm trying to say? So it's just, I'm just trying to help you understand the notation. We can further break this up. And then we can further break this up here. Hold on, I can do a little. Let's make it look good. Okay. Hold on. Hold on, class. I like things to look nice. That's better. Okay, so you see when you see this fourth order partial derivative, you see that and you say, okay, well, what order do I take the derivatives? Well, you can rewrite this fourth order partial derivative or fourth partial derivative as I have written it down here. So what do we differentiate the function with what variable do we differentiate the function with respect to first? X, because that's in the innermost parentheses. Okay, we get that partial derivative, then we differentiate that partial derivative with respect to what? What variable? What comes next? X again. Okay, and then we'll have another function. We're going to differentiate that function with respect to y. Good in. And then finally, at the end, with respect to z. So do you see how that works? Okay. All right, so now let me go ahead back to the example. Example 7, and hopefully now this will clarify what they're doing. So in the first step, when you differentiate with respect to x, you hold the y and z variables constant. Then the next step, when you differentiate with respect to x again, you hold the y and z variables constant. Okay. And then the third step, when you differentiate with respect to y, you hold the x and z variables constant. And then the last step there, when you differentiate with respect to z, you hold the x and y variables constant. Okay, so it's really no different than you're like all the derivative rules that you've learned are preserved. You just got to know what variables you're holding constant. Okay. Was that helpful? The whiteboard thing I did there, was that helpful for you? Good, good. All right. Thank you, Yunu. Are there any questions? Who's feeling good so far? Okay, Charles is. All right. Okay, well, Yunu's good. All right, well, let's do another example. Now, how many remember implicit differentiation? Implicit differentiation from Calc 1. All right, it's back. Ian remembers it. Yunu remembers it. Okay, so let's say, I have a nice example, but I want to just, yeah, I'll use that. Well, let's actually go now to the example here. The book has example 4, but I want to do this example here. Okay, something a little harder. Okay, so let me give you a moment to copy this example down. Okay, and all right, and then we'll go over it. Okay, so here we have variables x, y, and z related by this equation here. Now, implicitly, is z some function of x and y? You know, implicitly, well, hold on though. Okay, I'm getting good, interesting responses. I'm using the word implicitly. Is z a function of x and y? I'm not saying that we could, I mean, we could actually write z as a function of x and y, but I'm just saying, even though we don't have z equals, right? But what I'm trying to say is, if x and y change, does that cause z to change? So if x and y change, if you were to, here, let me put it another way. Let's say that x equals 1, y equals 2, and then we solve for z. Okay, so you agree we can get a z value, right? We'll call the z value a. Okay, let's say that I change y to 3. Am I going to get the same value a, or am I going to get some value b? Yeah, so some value b. That's right. So and if I were to change both x and y, what value would I get? Would it be a? Would it be b? Or would it be, okay, c? So that what you're telling me, and you know, occasionally we can get repeat values, but what you're telling me is that, Dr. Duty, z is a function of x and y implicitly, because if we change x, or we change y, or we change both of them, we're going to get a different value of z. As x and y changes, z changes. So it does make sense then to say, well, what is the rate of change of z with respect to x? You know, as x changes, how does z change? And what is the rate of change of z with respect to y? It makes sense to ask these questions. Now, we could try to solve for z. We could try to solve for z in terms of x and y, but it's basically likely impossible to do. Okay, so what we're going to have to do is use implicit differentiation. So let's go to the next page here. In the solution, what I do, okay, what I do here in the solution is I start off with you know, the equation, and now what I'm going to do is I'm going to differentiate both sides with respect to x. So I'm going to try to find the partial derivative of z with respect to x first. Okay. So let's make sure that you're comfortable with the third line here. So all right, so on the left-hand side, the partial derivative of x minus c with respect to x is equal to 1 minus the partial derivative of z with respect to x. You notice, class, I did not write 1 minus dz dx. I did not write that. The reason is because z is a function of two variables. Z is a function of x and y. And this means then that I have to use partial derivative notation. Now on the right side, what am I using to differentiate the right side? What kind of special rule? The chain rule. That's exactly right, Yunu. We're using the chain rule. Now when we get to the fourth step here, when we get to this fourth step, okay, well, I mean, of course, I have to find the partial derivative with respect to x of the function y times z. Y is being held constant, right? Correct? Y is being held constant. And what rule are we using here? What rule are we using here for this part? What special rule that you learned in Calculus 1? Product rule, that's right. So the partial derivative of y with respect to x is 0. Leave the z alone. And then the partial derivative, and then leave the first function, the y, alone, and then you have the partial derivative of z times partial derivative of z with respect to x. Okay, and so now, you know, here you go. You are now you know it works just like implicit differentiation that you learned before. Okay, it works the same way. You're going to group together the terms that involve the partial derivative of z with respect to x. And so I'm going to bring this term over on the right side, and that gets me here. And this is going to be my final answer. So I factor out the partial derivative of z with respect to x from the right side, and then this is my final answer. Please let me know if you have any questions. Okay, are we now we have the partial derivative of z with respect to x, and remember, this tells you how z changes as x changes, and you're holding y constant. But of course, depending on what your y value is, that's going to affect the derivative, and that's why it's there in the answer for this problem. Okay, are we ready to go to the next page? Okay. All right, very good. Well, then let me go to the next page. Now I'm going to do the partial derivative of z. Hold on, one moment. Ian, are you at your question is at the bottom here? Oh, well, what I did was I multiplied the top and the bottom here by 1 plus y squared times z squared. I multiply the top and the bottom by 1 plus y squared times z squared, only because, like, if I were typing this answer in WebAssign, it's a little easier to type this answer. WebAssign would take both, but, you know. Ian, does that answer your question? All right, show me, Ian, with your pen. Show me, let me just clear this here. Show me with your pen, or like, you know, you can like use the pen here. Okay, so, oh, well, what I did was this. Okay, I wanted to save a step. I got you. So this one here is this one here. What I did was I divided both sides of the equation by this. Yeah, and then I, you know, I kind of, yeah, no problem, good question. Okay, well now we're going to do the partial derivative of z. Hold on, the partial derivative of z with respect to y. And so I do the same procedure as I did the first time. And you will get this answer eventually. I didn't work it completely out for you, but this is the answer you'll get. Okay. Are there any questions? Okay. I'll stop the recording.